In this video, we explain what the concept of electromotive force is. So the idea is that up to now we've seen that if we have an electric current through a conductor, through a wire, we have and we have resistance there's a potential drop and we are losing energy. So we have a power loss. So if we want to maintain a current, we need some element that gives this wire some energy so that the current is maintained. And this is going to be the electromotive force. So to maintain a steady current in a conductor, we need a constant supply of electric energy. And this is what we call the source of electromotive force. And we normally use the symbol epsilon, the Greek symbol epsilon, to refer to it. So the first idea I want to put clear here is that even if it has the name force in it, it is not a force, okay? It's going to be the amount of energy per unit of charge, okay? So this is talking about energetics, okay? So a source of electromotive force is converting energy in other ways of energy, like chemical or mechanical, into electric energy, okay? It's going to support the current because it's going to give this conductor electric energy. So the idea is that this source of electromotive force is going to do work on the charges that pass through it, and it's going to increase their potential energy, and that increase of potential energy is going to be the electromotive force. So here we have a figure which is giving an analog between what the source of electromotive force does and and what the hand is doing with the different little balls. So the idea here is that when we get one of these small balls and we increase its gravitational potential and we let it free, this is the same that is doing the electromotive force. So it's getting the charges and it's increasing their electric potential, and then it's freeing them. So in this part, what we have is energy loss, okay? So this ball is bouncing here, and then at the end it loses all its potential, all its gravitatory potential, which in the analogy would be its loss of its electric potential. And then we need again the electromotive force to increase again its potential, so it can go through the charge can go through the electric circuit again. So this would be the analogy of an electric circuit, where the hand is the analogy of the electromotive force. So the electromotive force is the increase of potential energy per unit charge, okay? So if we know the electromotive force, we can calculate how much energy we are putting for each for an amount of charge. So if we have an amount of charge going through the through this source of electromotive force, then the total energy in being input into the system is the amount of charge that is going through the source of electromotive force times the electromotive force, okay? So normally it is batteries we're going to use. The batteries are what we're going to use in the electric circuits as a source of electromotive force. Okay, and the representation in circuits, the representation of batteries, is the one that you see here. So this represents the positive side of the battery, and this here represents the negative side of the battery. And these are the cables that connect to the rest of the circuit. Once we know the amount of energy that in a certain time is being put into the system by this source of electromotive force, we can calculate also the power input into the system. This is the rate at which the energy is supplied, and this is a power, and this is a gain of power into the circuit, and is going to be given by the change of energy divided by the amount of time that it takes to get that energy in. We had just seen that the amount of energy provided through for a time delta t was equal to the electromotive force times the amount of charge that was flowing through this source, this battery. Okay, so if we put everything together, we can see that the power input by the source of electromotive force into the circuit is going to be equal to epsilon, which is the electromotive force, times the electric current. Oh, sorry. So real batteries are not ideal. Okay, so in the circuit, sometimes we have to take into account that a battery is not ideal. What would be a battery, an ideal battery? An ideal battery would be the one that is going to provide the same electromotive force independently of how much charge is flowing through the battery through the circuit. So this represented in this scheme, this would be here in the y-axis we represent V, which is the potential difference between the both sides of the battery, and here we have the intensity. So an ideal battery would be the one that gives you this line here, because this would give you a constant differential of potential between both parts of the battery, independent of the amount of charge or the amount of electric current flowing through that battery. However, when you take real batteries, they usually don't show this type of line, but this one, in which what we have is a loss of difference of potential between the sides of the battery once we are increasing the amount of charge that is flowing through the battery. And this can be represented easily as this part here, which represents the ideal battery, with a little resistor located just next to the ideal electromotive force. So the real battery would be given by this part, where here we have the positive side of the battery, which would be at a potential VA, and this would be the negative side of the battery given by V sub B. So the difference of potential across the battery would be given by VA minus VB. This is what we normally call V, and what is represented in this graphic here. So this would be equal to epsilon. Okay, this is the increase of potential for a charge that is flowing through this battery, minus the potential drop in this resistor. And to know what the potential drop in that resistor is, we just have to remember Ohm's law. And Ohm's law stated that the resistance, which we're going to call small r here because it's really not very big, this resistance, is equal to the difference of potential between these 2 points. Okay, so we call it V prime because it's not the difference of potential between VA and VB, but only between A and this point here, divided by the electric current. So this V prime is equal to R, small r times I, and this is a potential drop. Okay, each time the current passes through a resistor, there is a potential drop given by the electric current times the resistance of the resistor. So this is what is taken into account here. So we can see that with this this small resistor of resistance R, small r, we have this type of behavior. Okay, this is more a real battery. And the last thing I wanted to talk about here is the total energy inside a battery. Okay, so if we think that the total amount of charge that the battery can supply is a big Q, then the total stored energy will be given by this big Q times the electromotive force. Okay. This energy, sometimes we can measure it in times of watts time hour. So watts per hour is also a measure of energy, because remember that power is equal to the amount of energy divided by the amount of time. So the amount of energetic, can be power times time. So sometimes watts per hour or kilowatts per hour are also a unit used to tell you how much energy a battery has stored.